Have you ever looked up at a massive suspension bridge, or maybe one of those towering construction cranes, and just wondered, how on earth do engineers know exactly how all those different forces balance out? I mean, how do they keep the whole thing from just tumbling down? Well, today in this explainer, we're going to take a super abstract mathematical concept, the Parallelogram Law of Forces, and we're actually going to prove it right before your eyes. We're using nothing but strings, some weights, and a really clever physical experiment to test the theory. Let's make the invisible visible. Here's our roadmap for today. First, we'll be defining the law, then looking at the clever setup, walking through the step-by-step procedure, analyzing the trials, and finally proving the law. Okay, Section 1, defining the parallelogram law. Let's get into it. Let's start with the foundational physics of it all. Here is the precise textbook definition straight from our source lab report. The Parallelogram Law of Forces states, if two forces acting at a point are represented as the two adjacent sides of a parallelogram, the diagonal passing through that point represents the resultant completely. Now, I know that sounds like a mouthful, but the absolute crucial word to focus on here is resultant. It really just means the combined overall effect of the two forces. Think of it like this. Imagine drawing two pulling forces as the sides of a box. The line that cuts right through the middle of that box, the diagonal, that tells you exactly where the combined force is going, and exactly how strong it is. Moving right along to Section 2, the clever police setup. Now, what's really fascinating here is this incredibly simple, but honestly genius apparatus used to test this out. We've got a vertical drawing board, right? And there are two pulleys mounted right at the top. Notice how weights P and Q hang over those pulleys, pulling outwards and upwards on those central strings. Then down below, we have a third weight, weight R, and that one is pulling straight down. Basically, these three forces are locked in a physical tug-of-war against each other until the entire system just stops. It finds perfect equilibrium. It's a literal tie, balanced right there in midair. Which brings us to Section 3, step-by-step procedure. So how do we get this physical setup onto paper? It's actually a brilliant bit of experimental design. Step 1, we pass the threads over the pulleys, attach our weights, that's P, Q, and R, and let them settle into that perfect equilibrium we were just talking about. Step 2, we slip a sheet of drawing paper directly behind those taut strings and very carefully mark their exact lines. Step 3, we take the board away, grab a ruler, and extend those marked lines until they meet at a single central point. We'll call that point O. Finally, in Step 4, we use a specific scale to mark the lengths of the lines based on the actual weights, draw out our parallelogram, and find our magic diagonal line, OC. We are literally tracing invisible physical forces and trapping them on paper. All right, let's look at the data in Section 4, analyzing the three trials. But wait, before we look at the diagrams, you really need to understand the translation key here. 1 centimeter on our paper equals exactly 50 grams of physical weight. This conversion right here, this is the magic key for this entire explainer. It's what lets us take a two-dimensional geometric shape and have it perfectly accurately represent real physical mass pulling on a string. So definitely keep that scale in the back of your mind as we go. 1 centimeter for every 50 grams. And this table brilliantly illustrates the results of our 3 experimental trials. Just take a second to look at these numbers. We tested completely different weights for P, Q, and R in each trial, but the absolute crucial thing to zero in on is the recorded data on the right side. Notice how the length of the upward diagonal, OC, perfectly matches the downward resultant line, OD, in every single trial. I mean, 3 centimeters matches 3 centimeters, 4 matches 4, 6 matches 6, and the angle between them? Exactly 180 degrees every single time. It is perfectly balanced. Let's actually visualize this geometry. It makes it so much clearer. Here is the geometry all mapped out for trial 1. So we used 100 grams for both of the pulling forces, P and Q. Since 50 grams equals 1 centimeter, those forces form the two 2-centimeter adjacent sides of our parallelogram. That's lines OA and OB. Now when we complete the parallelogram, the upward diagonal, OC, measures exactly 3 centimeters. And what was our downward force R? It was 150 grams, which, if we follow our scale, is exactly a 3-centimeter line, OD. So the 3-centimeter upward diagonal flawlessly opposes and perfectly balances that 3-centimeter downward weight. It's just beautiful. Let's see what happens when we scale things up a bit in trial 2. Here, forces P and Q are increased to 150 grams each, which gives us 3-centimeter sides. Now look closely at the central diagonal, OC.
It stretches to exactly 4 centimeters. And guess what? This perfectly matches the new 200-gram downward weight R, which is also plotted out as a 4-centimeter line OD. So, as we scale the weights up, the geometry just brilliantly adapts right along with it, maintaining the exact mathematical relationship predicted by the law. Now, you might be wondering, what if the weights aren't equal? Well, let's look at trial 3. Here we have completely asymmetrical forces, 200 grams pulling on the left and 250 grams pulling on the right. Because of this, our parallelogram is totally skewed, creating a 4-centimeter side and a 5-centimeter side. But here is the crazy part. The law still holds. The geometry still works out flawlessly. That diagonal OC accurately forms a 6-centimeter line, which perfectly balances the massive 300-gram weight pulling down. No matter how you warp the sides with uneven weights, the diagonal always finds the geometric truth.
Which leads us to our final stop, Section 5, proving the physics law. The whole aim of this experiment was to verify the parallelogram law of forces, right? And honestly, the evidence here is just undeniable, because the measured upward resultant, which is represented by our diagonal OC, always exactly equals the downward force OD, and because they are always sitting at exactly a 180-degree angle to one another, forming a perfectly straight vertical line, the system is mathematically and physically proven to be in complete equilibrium. The diagonal truly does represent the resultants completely. This math isn't just theory sitting in a textbook, it literally dictates physical reality.
It's actually pretty amazing when you take a step back and think about it. We took this dry, abstract geometric rule, and we just watched it perfectly dictate the physical reality of hanging metal weights in a room. So it really leaves me wondering, if simple strings and a few weights can so elegantly prove complex vector math, what other invisible mathematical laws of physics are operating silently around you right now? What hidden formulas are perfectly shaping and balancing the physical world you walk through every single day? Thanks for joining me on this explainer. Keep looking for the hidden structure in the world, and we'll catch you next time.